Okay, let me get started with this presentation. So we talk about silicon. Usually, because we have been working on this multiple scattering theory-based code, and we usually apply that to metallic systems. Because of historical reasons, because we are so used to with Muffin-Ting approximation, so we know that that works well for metallic systems. Then later on, we develop full potential. So we now thinking about this is time to apply that to non-metallic bonding systems, especially like system with a covalent bonding. Silicon is a good example. So I think it's time to consider this, and actually it takes quite some time to figure out. There's some issues appear, so it's not interesting to take a look at this and to talk about it. So because I'm going to record this, I consider that audience could come from different background. In case you already know this, you don't, just bear with me. And to have a little background about understanding of arbitral methods, because treating silicon has been, for other methods, this consider it's a solved problem. It's a never issue. But why take such a problem for us? Let me give a little background about consider if you consider since there are many different arbitral methods, we can tend to categorizing and put them into different categories. We either consider them either the all electron methods or pseudo potential methods. In all electron methods, both valence and core electrolytic states are calculated at each SCF iterations to solve the cont equation. So under this, there's different methods can be put into a subdirectory, subcategories for like based on the basis, like atom-centered local basis, where like KKR, LMTO, EMTO use that. So they use like a local basis to expand block wave functions. Or there's a local basis in the atomic volume. Then outside in the interstitial region, they use plane waves. So it's kind of hybrid basis, like it is done in APW and FAPW. In pseudo-potential methods, on the other hand, the core states are usually frozen, and it's not going to iterate. It's always pre-calculated and fixed. And the valence states are calculated for the pseudoized cont equation. It's not really original cont equation, rather with a pseudo-potential. In that case, the people usually tend to use like a plane wave basis, because for the serialized valence wave functions, you can expand that in the plane wave basis without using too many plane waves. Or we don't have to use any basis at all, like adaptive grids, finite elements. Of course, we have to have like we only treat that with kind of pseudoized wave functions so that it behaves well in space. That's why you can use this kind of a multi-grid method. Another category we can consider that is categorizing the arbitral method is that either approach is band structure approach or based on Green's function. The majority of the arbitral methods take band structure calculating approach to solve the cont equation, but basically just solve the cont equation directly to solve the wave functions and energy eigenvalues, which is band structures. And then the wave function is used to construct the charge density as shown in this formula. Right? That's general. Most people do in this category. There's another unique method. That's what we take. It's a Green function approach, focuses on calculating Green function instead of solving the cont equation. So electron density is then calculated from Green's function. That's what our approach is. Right? But seeing as Green function has certain difficulties, I'm going to talk about it. That's why it takes so long for us to attack this silicon, this kind of problem. Okay, now come to silicon. It's a covalent bonding. From the structure, you can tell like it has a highly the bonding has a certain directions that the lattice constant turns out to be around 10.21 atomic units. The private lattice is like a FCC-like, but at each lattice point has two atoms, as shown by these two colored spheres. One is at the corner, the other is at the radial direction. 1 quarter, 1 quarter, 1 quarter, 1 quarter. Okay. Now, if you look at the picture carefully, consider the layers 0, 1/4, half, 3/4, and 1. You look at from the top, you can see the location of the atoms. And if you look at carefully, you'll find that there's a large void in the structure. For example, at the half of the with the half means that at this layer, there's a large volume there. There's no atom. Okay, this circle here means the atom is at the bottom plane. So there's a large area which is not filled. And if you examine carefully, you'll find there's quite a large voids. So this brings a problem for those arbitral methods with atomic basis approach, right? With local basis approach, because in that approach, we expand the wave functions in terms of atomic center and local basis. Then, if there's a large void out there, and but your local basis is rather further away from the atom, then it will become problematic if you try to use the local basis to expand wave functions. So that's become a problematic. So the solution is quite simple, right? We just create a so-called virtual atom, but that of course z equal to 0. We just put that into treat them as atom. So we use that virtual atom as just like other atoms. So we establish local basis for that. So the wave function in those regions will be expanded by the local atom-centered basis. So that basically the whole space will be better represented. The wave function be better represented by those basis functions. So that's the idea. So that's how it is. People have done that in those local basis approach. All right. So in that case, the way we for silicon in particular, we find this large voids and we add two. It turns out you can add two virtual atoms. VA virtual atoms. Okay. The z equal to 0, so it's not real atom, but there's no atom. But thing is, we set up as an atomic center. All right. So they're just located in these two directions, two positions. So end up they fill out the whole space. So this is how it is done. All right. Okay. So actually, treating silicon is not a new thing for those local basis methods. Those arbitral methods with local basis. For example, here it's done in 1989 by full potential LMTO method. They got this nice parabolic curve by total energy versus the lattice volume or lattice constant. However, you're going to measure it. So this is diamond structure. That's what I'm talking about. This is silicon in diamond structure. Right? This is a nice parabolic curve, and but they're all based on band structure approach. Okay? They solve the Concha equation. They solve the wave functions and then construct the Chai density based on the band structure, right? For solving the eigenvalue. It's not a Green's function approach, right? And this is another approach by this group, R. Freeman's group in Northwestern. I think this group doesn't exist anymore. I don't know. I have to be careful because I'm saying this. This is going to be recorded. Anyway, so they got this nice parabolic curve with full potential KKR. They have their own version of KKR method. But this is based on the band structure calculations. Okay, so they get this nice parabolic curve and calculate between this. Unfortunately, this is in the angstrom units. Anyway, so this is done. It's 1995. All right, so this is based on band structure calculations, we already have silicon results. How about Green function approach? Okay, so let's give it a try. We have the code. I just turn on the Muffin approximation because it's easy, fast. And what I found is we got this. Just when you change the lattice constant, you don't get a parabolic curve. Rather, you have to see these things just going down the hill. The energy keep on decreasing. That's not what we expect. We expect the energy has a minimum value near the equilibrium lattice constant, and so further away from that, you get a high energy, right? That's what we would expect. Thanks to Franco, who sent me this result. He ran a different KKR code. They got ASA KKR. This is a result he get, and you see that's totally opposite to what I found for the Muffin approximation. This ASA is that there's a unlike Muffin, the sphere do not touch. Right? ASA just have touching spheres, but each volume takes the same volume as the atomic cell volume. So you end up the sphere touch one another. But anyway, that's what the result he has. He shows when you increase the lattice constant, energy increases, keep on increasing. So it's totally opposite to this. So this is just totally from our mind. What is going on? So this is the kind of result we get. But this is we can blame on spherical approximation, right? It's easy to blame because of course we need to try full potential. Okay, so let's talk about the full potential. Obviously, we will think full potential is needed because it's because of covalent bonding, right? So in that case, of course, because of that bonding nature, Muffin approximation is no longer appropriate. So then we want to try Green's function method. The problem is where the difficulty coming from? Why it takes so long, right? For so many years, we have almost never thought about how to do this in full potential. The main reason for that is, despite the Green's function itself is a very elegant mathematically, and also is a formally exact method. Formally, I'm not talking about numerical, but approach. The theory itself this expression is exact. Okay, so the basic problem is in the full potential case, this irregular solution is very difficult to calculate. Basically, when you solve this irregular solution, starting from the outside, from the atomic cell, you have a nice boundary conditions. When you solve inward, you end up, when you approach the origin, center of the atom, the center of the cell, or near where the atom is, near the nucleus, the regular solution will blow up because it's irregular solution. But seeing as the error, numerical error, is very difficult to control, it becomes problematic. You can get a kind of solution, but seeing it's not forming a proper Green's function. So that's kind of difficulty everyone faces. Okay, some people will choose. Okay, I'm not going to calculate irregular solution all the way to the center of the cell. Rather, I'm going to stop somewhere. Then rest of the part I'm going to extrapolate. Well, that's one technique people use. But the other technique, the technique we use is different, right? So what we do is, I think I showed this slide before in some other presentation. I'm going to show that again just to remind us what is we are doing. Okay, so let's take a look at single-side Green's function. The difference between the single side and the multiple scattering Green's function is that the single side will have a T matrix here. Okay, everything else is the same. This is just single side scattering matrix. The other is a tall matrix. It's multiple scattering. All the other functions are exact same. There's a unique, there's an important feature about this. That when epsilon is on the real energy axis, the imaginary part of the first term is non-zero if epsilon is greater than 0. Right. So that is, if epsilon is less than 0, the imaginary part of this is 0. Okay. Secondly, when the epsilon is on the real energy axis, the second term is real. There's no imaginary part. When imaginary part is 0. So the imaginary part of single side Green function on the real energy is thus given by this. But when I take imaginary part, because this imaginary part on the real energy axis is 0. So because I'm only interested in imaginary part, so I end up only use the first term. So that can avoid the second term because I'm not interested in the real part. Right? I'm only interested in the imaginary part. So I can ignore the second term. If I calculate that Green's function, try to calculate the imaginary part on the real axis, it turns out only need the first term, the regular solution term. And also, as I said here, that when epsilon is less than 0, the imaginary part is 0. Okay, the green function is essentially is 0. So that's kind of important feature. Because of that, we can do the following to do a full potential. All right. So put this in such a consideration that look at energy complex plane. There's a real part axis and imaginary part axis, right? So if you consider that, the valence states will be following between bottom of the valence band up to further, positive part. We are only interested up to like Fermi energy, all right? And then below the valence band will be the semi-core and the deep cores. That will be calculated with a different technique. That's not what we are worrying about here. And then what we do is we calculate using different technique. I think I talked about this before. We get the core density states, and for this part we use the green function technique to calculate valence density states. Valence charge density, we add them together is a total charge density. That's what we calculate. For the valence charge density, a general way we do that, especially in the Muffin approximation, what we do is we draw a contour so that we can integrate the green function along the contour to calculate valence density. That's how we do it. But the problem is, on the complex energy plane, we have a difficulty to deal with the irregular solutions, right? So the way we avoid doing calculating irregular solution is we just calculating the difference between the multiple scattering term and in the single side term. This difference is only involving the irregular solution term. The irregular solution term just cancel with one another. Okay, so that part can be done along the contour. Then, of course, we have to add a single side green function back to it. So that's how we do this. Okay, so these two things add together is the total valence charge density. All right. How about this part? Why are we only starting from integrate from here to here, not from here? The reason for that, because I explained in my previous slide, because imaginary part of the green function, single side green function, for epsilon less than 0 is 0. So this part doesn't, appear. All right. So we don't need it. So that's kind of argument. All right. So it's implementing our code. I thought this is a good time to start. And so basically the whole idea, the way we do that, so we can avoid the irregular solution. So that's our approach to the full potential green function approach method. It's different from other groups what they did. All right. So now we have this methodology. Now it's a time to apply to silicon. All right. We have done this for other metallic systems. It works fine. All right. Now silicon failed because it doesn't. the calculating does it just doesn't work well. It doesn't work right. It's not even converged. So it doesn't make sense. The result essentially doesn't make sense. Right. So what was the problem? It turns out this statement has some fault, some problem in it, because even though the imaginary part is this 0, the integration is not 0. The reason for that is the single side green function could have a pole. So even though imaginary part is 0, but if the green function itself has a pole, when you do the integration, it's going to, by residual theorem, right? That's going to contribute. So that's exactly the reason for that, because for silicon, found something very strange about that. It has called a shallow bound state in this region that contribute certain values to the integration when you take the imaginary part. Okay, that's complex analysis. Tells us what is going on. So actually, that's because of the s electron on silicon is contributing a pole to the single side Green's function. That makes this integration non-zero. And many other metallic systems don't have the shallow bound state. So it never appears such a problem to be a problem. But unfortunately, for silicon, it does have the problem. So we'll have to take care of that in general way. So no matter in the future, so whatever one system, we always need to check if there is a shallow bound state. If there is, we'll have to take care of these things carefully. All right. Okay. So our approach we take the following step to improve this Green function integrating technique. So first of all, we have to determine if there are any shallow bound states associated with each atom, right? So if this is just purely single scattering problem. The same technique can be used to calculate. I think I talked about this for the core states. When we use a Green function approach, we always try to figure out if there's bound state, and we use a Green function to do that. We have done that for the core state. Surely we can do that for this part of area. All we have to do is just figure out where the bound state is. If there is bound states, determine the bound state energy. And then we know the bound state energy, where that is. You draw a little contour around it. It takes only a few energy points along that to get the integration of the single side Green function down. Then we can add the result to the other part of the single side Green function integration from 0 to Fermi energy. So that's part that had to be taken care of. So once that, we can get this. Okay, it looks much better now, but it's not quite. This have a little jiggering here if you enlarge the picture, and also there's and once you go to like 10.5, the energy suddenly dropped to here. So it looks very, very strange. Why that happens? Right? So it's not quite completely right. Another thing is, for calculating also failed to converge if its lattice constant is greater than 10.45. If for a larger lattice constant, you're never going to get a converged result. That's the problem. So what is going on? So it's not, we have not solved the problem quite right yet. All right, but we are getting close. Of course, if you want to hide this kind of skeleton in the color, what you can do is just don't consider that. We only calculate up to this point. And you get a nice parabolic curve, right? You can publish the result, say, hey, I'm done with it. It works. But this is a hidden problem here. We need to figure out what really going on, right? So we cannot hide the problem. We need to find out where the problem is. Okay. So it turns out in a Fuchs-Taylor KKR method that we use, the unit cell, the entire unit cell, the space is divided into non-overlapping atomic cells, right? As I expanded some other time, and each contains a single atom, or either silicon, or in this case, or virtual atom, empty cell. Right? When we do this space division, we give each atom the same size. Say, just like set up like a big size cell, right? When you have two atoms, you put a plane in between, we just put it in the middle, right? That's how we do it. Just we call the plane called radical plane. Basically, the distance of the radical plane have same distance from other atoms, no matter what their atoms are. So we just have the same. We'll put that plane just right in between. Actually, you can think about carefully. Why would I say that if there's a virtual atom, right? That actually z equals 0. Why would have that take such space as large as silicon? You can certainly move that radical plane further closer to the empty cell, right? Because why would you give it larger space? And also for some heavy atom, why would that taking the same space as the lighter atom? It might give a heavy atom because they have more electrons. You should give them more space to breathe, right? So so certainly this process has issues. We need to so keeping like a silicon and the virtual atom the same size is certainly not appropriate. All right. So because of that, I take a radical approach that I take a silicon almost twice as big as the virtual atom. So I choose that ratio to be 2.2. It's I just made this up. I just did that. Once I do that, I get a very nice parabolic curve. Okay. So that all seems like working properly now, and also calculate density states. It looks also very sensible. And what you can find is a band gap here. The band gap, if you look at closer carefully, what you find is band gap, experimental band gap is 0.086. And this band gap is 0.033, as what we expect, because for LDA calculations, you underestimate the band gap for silicon. So, and which is comparable to other arbitrary methods. Some others getting, about 0.03 some 5 or 0.03 some other number. It's always like a couple of milliripple difference. So which is very good, very sensible. Okay, so we got a very good result here. They all look nice, working properly, seems. Now, thanks to Franco, he did the EMTO calculations. I believe that's Green's function approach. I don't know. Maybe I think EMTO can do band structure as well, but I'm not sure. Franco can tell me if this is a Green function or band structure. But anyway, that's an EMTO result. That's that. No, I'm sorry. This is not EMTO. Sorry, this is different slide. That's the next slide. For this slide, I think okay, because I changed the volume of the atom, I should give a Muffin another try, right? So before I show the Muffin result, because they all have this equal volume. So now I'm going to give give a fair try for Muffin method. So what I did, what I have done here, I use the same kind of radical plane ratio, but that run Muffin calculations. So this I got also not unlike what I get before, that energy keep on decreasing as I have larger lattice constant, but rather I get seems like getting a parabolic curve, except there's some kind of jiggling around here. It's not quite smooth, and also this this is not quite something still not correct, right? And also this minimum lowest energy point is not closer to the lattice equilibrium lattice constant, which should be here. This is a lattice equilibrium lattice constant, but rather Muffin calculation kind of underestimate the equilibrium lattice constant, which is shown to be here. It's about 1% off from the result, but it's still reasonably good. So interestingly, even with Muffin calculations, by properly setting up the size of the atomic ratio, volume ratio, you can still get a kind of this kind of curve. Of course, there's some issues with if you ignore that, you just can only pick up a few points, which seems like working properly. Okay, so this is kind of something I want to show. So now, okay, thanks. I was talking about these slides before this. Franco had shown me this result. This is an EMTO calculation. He chooses the ratio to be 1.25 in this calculation. So this is an EMTO result. But what's unknown to me is I don't know if it's a band structure or it's a Green's function. But that's I'll need to check.
It's a Green's function approach.
It's a Green's function. Okay, excellent. That's good. That's nice. All right. So this is a Green's function result from EMTO. It looks very nice, smooth. Okay. So now, in summary, let me see. Okay. The full potential or full charge density is needed for average calculations for silicon. Obviously, even though I tried for Muffin, I showed this. It's not the result. It's not very satisfactory, and so obviously we have to do full potential. The empty cell volumes need to be. We need to use empty cell volumes to fill up all the voids. It certainly is necessary, but the size needs to be carefully determined, right? So how we do that? So it is necessary now to consider a general approach, because by default, what we run calculation is always give an atom this equal size. Just put the radical, when you divide the space, we always put the radical plane just right in between atoms. I think now we need to reconsider this procedure. Rather give different atom a different weight, a different rate. When we put the plane is. So what's the kind of general approach? One possibility is, of course, we know there's if you look at any atomic chemical element or atomic property tables, they usually show atomic radius, right? That radius could come from different sources or different techniques, but they have that kind of information. So we can use that kind of data to determine what's the ratio of the radical plane when we set up this cell, atomic cell. That's one approach. Of course, there's an alternative suggestion is to by setting put the plane at where when we calculate the charge density, we can find where the maximum or minimum is, which is in between two atoms. Then we just put that plan there. So that requires each iteration we have to reset the radical plan. I think that's a very sensible way to do it, because that makes more physical sense. That we just put the radical plan where the physical has certain physical meanings. I think that's what very interesting approach. So of course you have to adjust this each time. So that means you have to recalculate step functions at each SF iteration. Unlike currently, we set up the size of the atomic cell. We always fix it. We never change it. So we only calculate step function once. But with this approach, that requires, because we always readjust the radical plan, the atomic cell volume and size shape will be different each iteration. So then you have to recalculate step function. Okay, so I think that's also very interesting approach, but I think we need to take a consideration. So that's all my talk, and now we're going to stop for today. Let me see if I can stop recording.